Well, it looks like we can start. Welcome back, everyone, and happy almost weekend. We're getting across the 75% mark for the entire semester as well. And we took a good amount of extra time on our Chapter 5 statistical reasoning. So it might turn out that Chapter 8, this could be the last chapter for our course. We'll see where we end up with on working through these problems, but we're going to make sure we're not trying to race through any of the content just to try to fit in every little thing. So far, we're on the third example of the exponential growth, exponential decay section, named as doubling time and the half-life. And as far as the quizzes go, we have quiz number 10. This is based off our graph section in chapter 5, due today. And our new quiz number 11 has been posted. Because we only started unit 8B, this quiz 11 is based off a unit 8A problem instead. But that's what we have going on for the moment. Like we've been mentioning, I'll be working after getting caught up on grading on posting the exam 3 information. Same kind of things we did for both exams 1, exam 2, the exact coverage and the review problems. But any questions at all, folks, before we get started today? Okay, well, this section here, it does have a good amount of formulas that we're trying to track through. We're going through our first set of looking into the exponential growth model, as well as the doubling time itself and the approximate doubling time. And here's where we left off on the start of these notes. So we had another set of notes at the very top, set of formulas rather, that told us that if something is growing with a doubling time, it's growing exponentially, and it's growing at a factor of 2 to the power, this is the exponential portion, time divided by t double. So this is the growth factor after an amount of time t. It multiplies an initial value, and that gives us the size of the thing that's changing at an amount of time t. So we'll be using this formula a good amount. But the tricky thing about using this formula is plenty of problems give you information that does not provide a doubling time whatsoever. And that's where this approximation comes into play. We'll be looking into the exact formula as well, but plenty of the problems we'll see in the homework are just based off using the approximate doubling time formula, the one above. So if a quantity is growing exponentially at a rate, p% is how our author dubs the rate in this context, the doubling time by the so-called rule of 70 is 70 divided by p, where that's not converted into a decimal number. So that's what we looked into for the gross domestic product of Panama. They are growing at a consistent rate of 4% per year. So if they continue to grow at that rate, p is 4. All we've done is taken off the percent symbol, divide by 70 by that value 4, and that gave us the 17.5 years. So we're estimating if they stay growing at that consistent rate, the economy is essentially doubling its size every 17 and a half years. So that's where we were right at the end of class on Wednesday. Now we're going to go forward and address an additional question: how much the economy is going to grow by in 5 years. Any questions at all with the recap first before we address this side? Okay, another tricky thing about our set of formulas is that usually it feels like we should be using the entire formula to get a new value out. But plenty of the questions in my lab, so we duplicate them here in the notes, don't even give you an initial value. All we're trying to do is find out the growth factor. So when it says by what factor will the GDP increase by, we're just doing this part, the second half of the formula, and nothing else. So let's put this down on the notes. The growth factor is going to be 2 to the power amount of time t divided by t double. The doubling time is in years, and the question, the time t itself is in years as well. So we have compatible units, we don't have to make any changes. So t is 5 years. And that means this quantity is going to become equal to 2 to the power of that 5 we identified in the context, divide by the doubling time, which is 17.5 years. And it looks a little bit weird because it doubles every almost 20 years, but the question's about 5 years. And that's okay. If we're just interested in the short run, we can use the doubling time to still answer the question of how much it's growing in those 5 years. So that's what we would put down on paper. This time, it's not asking us to format our answer as a number in exponential notation. Here, we're just going to plug the whole thing into the calculator and get an approximation out. So next step, in a typical calculator, I'll use Desmos as usual for our computation. Just put in 2 to the power. Make sure you have parentheses around the whole exponent, or maybe calculate it separately and plug in the answer. 5 divided by 17.5 to the nearest hundredth is a 1.22. So that's the growth factor of Panama's GDP in 5 years. Well, any less questions at all, folks, coming up with that number? Okay, this whole problem is resolved once we got the number. So there's no further analysis we're doing on it. But just to get a good feel for what we even computed, sometimes that's the harder skill. Let's just put down something in parentheses. Said differently, this means the size of Panama's economy grows by, if it's going to grow by a factor of 1.22, that means it grows by 22% in 5 years. So if it's growing 4% per year, it's not going to be 4% times 5, because every new year we take 4% of what the current GDP is. It's a little bit more, 22% in those 5 years. If we let 17.5 years go by, it would have been an entire 100%, since that would have been the doubling time. Well, any last questions at all, folks, on the conclusion for part B? Okay, again, this question is weird in the sense that they didn't tell us what the GDP even was for Panama. We're just wondering how much it's growing by. We don't know what its new value is going to be. But so plenty of the questions do want us to calculate a new value based on some initial value. So let's see what's going on in the next context. For example 4, I think we can put this on the next page. We're looking into the consumer price index. Same kind of concept as we visited all the way back in chapter 3. If we look into the table for the CPI, we can find that it was 218.1 in the year 2010. So that means the approximate cost of goods, services, housing, and so on was about 218% that of around 1980, a few base years really. What we know a little bit more, in that year, the CPI was growing at a rate of approximately 1.7 per year. So we have a growth rate in the problem. If it's growing by that amount, that means exponential growth. That's what we were learning about in the last unit, 8A. It's not growing by a fixed amount of, say, 20 points per year. It's growing by a relative percentage amount instead. So if it's growing at a 1.7% per year, that's really an inflationary number. And those were the kinds of things we were looking at way back in, actually not that far back, pretty recently in chapter 5. So we were looking at the percent change from previous year. This is really just inflation when we were looking at that percent change of CPI. And in 2010, it was a 1.7% change. So we're looking at this one little node right here in the bar chart. But now we have a different question we're resolving. We're wondering if it's growing by that rate of 1.7%, what then is going to be the doubling time for CPI? When is it going to completely double? So here it says, how long would it take for the CPI to double? You know, for a good question like this one, I think MyLab would also say this as well to direct us to the right formula. I'll try to be very specific if this comes up as an exam problem. Use the approximate doubling time formula. This will be helpful for us to know which formula exactly we're using. Sorry for the omission here. I'll try to make sure that this definitely gets asked on a real exam question. It's good to know what formula we're using in the first place. The approximate doubling time formula would go T double is approximately 70 divided by the growth rate, P. So this is really just telling us to use the rule of 70. Then once we have this formula down, all we do is we take P as 1.7, dropping the percent symbol, but not moving the decimal. We leave it exactly as a 1.7 for this one formula. So this is 70 divided by 1.7. So now we just go to a calculator. This one is going to be rounded to the nearest tenth of a year. And we have an approximate doubling time. This approximation is pretty decent. The rule of 70 is accurate as long as the growth rate is at 15% or lower. More and more accurate the smaller it gets. So this is not too bad of a value. So altogether, 70 divided by 1.7, whatever their unit was for time, this is 1.7 per year, is going to be the unit for the doubling time. So this one will be 41.2 years after rounding. So if the growth rate, say beyond 2010, for some weird magical reason, if it never changed, if CPI continues to increase by 1.7%, then it will double every 41.2 years. Any questions so far, folks, with part A? Okay, well, here's the new thing about this problem. In the last question, we didn't know Panama's GDP whatsoever. We just knew by how much it was growing. But we do know the consumer price index for 2010. It was 218.1. So this is considered to be the initial value in the problem. And part B asks, again, making a big, probably not super realistic assumption, but if we make that assumption, if for some reason the rate stays at 1.7%, stable every year after 2010, what would be the value of the CPI in year 2025? So basically a what if question. If it was nice, low inflation, all this time, what should CPI be at? Right, well, last year, not quite right now any longer. So we can address this part by saying, here's our formula from the very top of the notes. The CPI in year 2025 is going to be the new value. It'll be equal to the initial value times the factor by which it's growing. So this is times 2 to the power of T over T double. So there's our full formula. This time we're using the entire thing. We need to make a check on our units. T, well, it's not going to be 2025 because 2025 years haven't gone by. We're just saying how much time has gone by if we're going from an initial value at 2010 to the new value in 2025. So T is 2025 minus 2010, or in other words, just 15 years. And our doubling time is in years as well, so no unit conversions like we had to make on our first example. So the new value is going to be CPI in 2025. This is going to be the CPI as it was in 2010, 218.1 times 2 to the power of 15 years, divide by the doubling time. So it's not going to double by this assumption of stable growth rate, 1.7%, because 41.2 years haven't gone by, but it's certainly increasing, and this will tell us what it increases to. So that's our brand new computation to take. It's exponential growth because there's an exponential function right here, 2 to an exponent. Any last questions at all, folks, before we throw it in the calculator? Okay, so last step, just crank it out. Last thing we're going to do is put in, let me know if you're having any issues with the calculator. It's not a bad idea to do some of these things like the exponent and the stages to just make it easier to put in the calculator. If you do approximate that, 15 divided by 41.2, just make sure that you carry a lot of digits. Because if you round too bluntly, say to 2 decimal places, we could potentially lose the question in MyLab by being quite a bit off with an exponential. So if you round first, probably go to 8 digits for a good measure. Here, to be extra cautious, it's sometimes the best idea to just put it all into the calculator in one go. 218.1 times 2 to the power 15 over 41.2 gives us that amount. The new CPI is estimated to be, let's see, we're rounding to nearest tenth again, so 280.7. So there it is, our brand new CPI value. But again, it's making a really, really strong assumption, assuming that inflation is exactly stable, never changing from 1.7% over the course of 50 years. No matter how bad the world gets, the global economy destabilizes. So that's a humongous assumption. But again, it's a what if question. And we're saying, what if it stayed stable? This is how low the CPI would really be. Now we can check some other information because we've looked into these kind of matters before. Amy says, do we only use this formula with exponential growth? Yeah, absolutely. If we're looking into exponential decay, the formula looks actually really, really similar. But the only change is if we're doing with decay, that 2 right there becomes a 1/2 instead. And we don't say doubling time, we say T half for half-life instead. So it looks really, really close, but there's a small change in this one spot. So those are going to be the next waves of formulas that we're going to take a look into next. Other questions at the moment? Okay, now that I think about that, that's a good comment to make here. Only use for exponential growth. So that formula is relative to just things that are growing. And we'll see things that are decaying, just like in the last unit, 8A, like in the caffeine problem, for example, coming up shortly in these notes as well. So just to take a bigger look at the context of this problem, we had pretty accurate information that 2010, the CPI was really 218.1. It really was growing at the inflationary rate of 1.7% per year. But if we look again at this graph, it's telling us a different story. Inflation rate is stable at 1.7% after 2010 is a fiction, right? It nearly doubled in the next year, then it slowly came down. It was a little bit below in the next following years, 2013, 2014, drops to a near zero in 2015. But then it really started getting going, except for 2 years, 2016, 2020. It skyrocketed in these years, the global pandemic probably having something to do with that. And we'll see what it turns out to in 2026, but it's still high in 2025. The majority of growth rates were almost all larger than the 1.7%. So that means our CPI estimate of about 280.7, it's got to be way short. In fact, it is. If we go to our original CPI table, it was 321.9. So we are estimating extremely low if we're assuming a stable growth rate of 1.7%. Nonetheless, again, it's still an interesting what if calculation. We can say what happens if we made that assumption. What if that was really true? Where would the CPI be now in 2025? I keep wanting to say currently, but we don't have that data yet. Well, let's take a look into the next example, looking into these kind of matters of exponential change. And looks like we're getting into the next concept for exponential decay. Once again, there's just one small change. We're looking into exponential growth. We have the growth factor here, that's 2. Things are doubling. And this is kind of convenient and nice in a way. The algebra lines up nicely to, for dealing with exponential decay, that means we have a half-life in the problem that we're interested in. Things are decaying. We want to know when does it decay to half of its initial amount. And the formula is almost totally identical, except we have a half right there. So that's the one and only change. As well as, of course, we have a half-life here, t half. So let's indicate the information just like we did here on this. We have something that's decreasing. So let's change from increase to decrease right here. So after a time t, an exponentially decaying quantity with half-life t half will have decreased in size by a factor of 1/2 to the power t divided by t half. So this is the increase factor, but now we're looking at the decrease factor here. And we will say the new value is going to be an initial value. Let's highlight that as before, times the factor by which it decreases, 1/2 times t to the power 1/2. So although there are a lot of formulas here to track, they're kind of nice in a certain sense. If you know you're growing, that means something's doubling. So 2 is representing that doubling. If you know something is changing exponentially but decaying, that means you're halving things, and there's the 1/2 in the formula. Well, we're going to practice these formulas just like we did on the prior examples in a similar kind of way. The questions will be similar again in not WebAssign, but in MyLab homework system. Some of the problems focus on the decrease factor. Other problems focus on the new value with an initial, initial value also given. Okay, let's get started on this new slew of formulas to take a look into. These problems are tricky in the way the wording is given. I copied the wording pretty similar to how these are being stated in the textbook as well as MyLab as well, just to make the notes similar. But when it says what fraction, our answer is not a fraction. In fact, we're going to round it to our nearest hundredth. We're giving a decimal number. So it seems like the instructions kind of are arguing with themselves when it asks for what fraction. The reason it's phrased this way, which is, again, to me, pretty awkward, is because we're thinking of that right there as the fraction, 1/2 raised to some power. So just to help with the wording a little bit, think whenever it asks for what fraction of the trace or dose remains active, we're asking really what factor is something decaying by. So this is the fractional decay. So really strange wording on that. So we'll try to emphasize that as we're going. seems to be asked again on the next part B. And here's the context of this new example 5. All these next examples are going to be about something decaying exponentially. They can be populations like E. coli bacteria, or maybe some other kind of animal or organism. But they could also be more abstract things like areas, an area a plant is covering as it's taking over something, or an area of something shrinking. And this one's even different. This is just a concentration in the bloodstream. So the context here is about a certain kind of scan called the DAT scan, which is a real imaging test specialized to evaluate the dopamine system in the brain. So we're imaging the brain with this kind of scan. It is primarily used by doctors to help differentiate between Parkinsonian syndromes. That's a new word for me. What that means is conditions that are similar to Parkinson's disease and other very similar conditions. So we're looking to evaluate symptoms similar to Parkinson's disease itself and a whole slew of other kind of rough disorders. To do that, they have to image your brain, the dopamine systems. And that means they're using a radioactive tracer. This is something that gets injected, enters into your bloodstream. Eventually, it'll cross a blood-brain barrier, and now they can take an image of your brain and look into these structures. So a radioactive tracer used in neurological scans, such as the DAT scan for Parkinson's, is that chemical. This involves some kind of radioactive isotope of iodine, called specifically that, loflurplane I-123. The half-life of that tracer is 13.2 hours. So we've got a half-life, so that gets us started here. I can say right away, getting going on this context, that the half-life, T half, is 13.2 hours. So that gets us started. Now that we know the half-life, we can say someone is injected by some amount of this medical tracer. The half-life is pretty short, so it's being expelled out of the body somewhat rapidly. We want to know if they had this tracer, maybe they did the DAT scan as well. How much of the tracer is left in your bloodstream after 60 hours? So that's our full context, the full problem we're going to take a look into. Any questions at the moment before we jump into the computation? Okay, so all we really do on this particular problem is we don't have an initial value. We're just wanting to know by what fractional amount is the initial value really changing? What's the decay factor, in other words? Kind of similar to what we were doing in some of the prior exercises. So all we have to calculate this time is 2 times t to the power, 2 to the power of t divided by, rather, t half. So once we get that value, we'll be done with this question. Also, some of the questions asked us to leave it in exponential form, but on this one, we're just going to round this to the nearest hundredth once we throw in the values. So the value for t is provided here. The time is going to be 60 hours. We always want to double check units. The half-life is in hours, so that's compatible. We can just drop in the information here. This is 2 to the power of 60 hours have gone by. The half-life is 13.2 hours. So this fraction will tell us what is remaining after those 60 hours go by. So pretty fast computation. Let's throw this in. 2 to the power 60 divided by 13.2. So rounded to the nearest hundredth, this is 23, or excuse me, that's not quite right. That would have been doubling. Don't forget, I forgot one big part right here. Don't do as I did. Let me start over. Rather than 2, this is a 1/2. Must have gotten too familiar with the pattern of the last problem. Sorry for that omission there. Let's put in just a stark warning about this one. Use 1/2 for exponential decay, or in other words, half-life problems. That's definitely a silly error, and we could tell probably something is awry if we are saying there's going to be effectively 23 times the amount of the tracer 60 hours later. That's probably lethal. It should be going down in the bloodstream, not going up. So let's try again after that misadventure. Take 1/2. Now we're following the format of the actual formula there. Raise that to the power of 60, divide by 13.2. And that looks a little bit more realistic. Rounding this one to the nearest hundredth would give us 0.04. So we did it, folks. That's, again, really awkward in the wording. We're thinking of this as the fractional amount, 4/100ths of the medical tracer initially injected remains in the patient's system, in their bloodstream of their tissues for 60 hours. So we did it. It's definitely diminishing. It's being cut in half every 13.2 hours. And so they'll be completely gone from the system essentially before they know it. Any last questions or thoughts, folks, getting through this one? Okay. And just returning back to the weird wording, this is something we just have to stick with because our textbook seems to use this wording. My lab carries it over, and that can't be changed from the problems, unfortunately. When it says what fraction, really what we found was a proportion. That proportion, we could have changed into a percentage if we really wanted to, and we could have said 4% of the tracer remained in the bloodstream after 60 hours. If you were doing this problem on WebAssign, they want the decimal number. But if you did this as an exam problem and you said 4/100, because you're really thinking about a fraction, that's completely correct as well. In the interpretation, we can once again say 0.04 converting to a percentage is 4%, which tells us 4% of the tracer is left in 60 hours. So there's a lot of different ways to interpret what we just computed. But thinking in terms of the specific formula, this is the answer that we're usually going to format it for the purpose of homework. Well, the next question is asking, if we're looking at the same patient that had this procedure done, they got loflurane injected, radioactive isotope of iodine. I think this is iodine 123. But it's 1 week later since that injection. We want to know what fractional dose of the tracer now remains if 1 entire week has gone by, not just 60 hours. Half-life is pretty impressive in its own. If enough time goes by, the value gets really, really close to 0 quite rapidly. Contrasting against exponential decay, where things start to blow up and the model actually breaks down very rapidly in short time frames if things are growing fast enough. So here, the big warning on this one is, notice that there's a mismatch on the units. T equals 1 week, but we can't put 1 week divided by 13.2 unless we've converted it into actual hours. So we have to match the units that we see here. So let's start by saying if T is 1 week, then we know that there's, well, 7 days per the 1 week. We have to get this all the way down to hours. So we also know that there's 24 hours per the 1 day. Again, this is just really revisiting our skills in chapter 2. The unit analysis will allow units to cancel from numerators to denominators until all we have is something left in hours. And this boils down to just 7 times 24. And again, you probably knew that if you just went 7 times 24, got 168 right away, that's fine as well. You don't have to show the whole unit analysis. This is just helpful when things get tricky. And we wanted to be extra sure we're actually multiplying by 24, not dividing by it. So 168 goes in hours. And now we can rewrite this entire statement as the 1/2 raised to the power of t divided by the half-life. Our author uses t half for half-life. And by the way, if you don't like that symbol, t half being the half-life, a more common symbol is the Greek letter lambda. So if you prefer to use that, that'd be completely fine. But I'll keep with the actual values that the author used in the reading as well, keeping it in that format. So this will be 1/2 to the power of 168 hours divided by the half-life, 13.2 hours. And notice the further instructions. It says, express the answer using scientific notation, 2 significant digits. So it's a bit of a review problem as well. This part of the question is kind of necessary because in exponential decay, 1 week is a really long time for 13.2 hours. So our number is minuscule. But that should be the case for a good medical tracer. It shouldn't stay in your system for a long, long time. So our amount is going to be 1/2 to the power of 168 divided by 13.2. And there's the quantity. This is the fractional amount in decimal form, or the proportion of the tracer remaining after 1 full week. When it says 2 significant digits, it means we're only going to carry in the 1/4. The digits to the left of this 1 would be considered non-significant. So it's 0.00014. But we also want to write this in scientific notation, so that's going to be our next step. Re-express this as 1.4. That's a decimal shift to the right of 1, 2, 3, 1, 2, 3, 4 places, just double checking there. So that means we have to multiply by 10 to the power of -4. So this is the amount or the proportion or the fraction of the original tracer, if you use the original language, remaining after 1 whole week. Well, any last questions or thoughts, folks, getting through this question here?
Yes, I have a question. Do we round that up? Would it have been to 0.15, or do we not round it up?
We would have rounded it up. Good eye on that one. I completely missed the 7 on that. So I would say if you're doing this as a homework question, doing this as a quiz question or exam question, I wouldn't have been too picky, but it would have been annoying as a MyLab question. They are picky with the rounding. So thanks again for spotting that. This rounds up to a 5, so let's fix that here. Approximately 5 on this one. So a 1.5 as well. And yes, absolutely, good eye on that. Whenever we're using significant digits, if we're told to take it to 2 significant digits, the common interpretation is round as we write in those 2 digits, just like as you mentioned. Again, thanks for mentioning that. Any other questions at the moment? Okay, so again, you could call this the fractional amount remaining or just the fraction remaining, or you could call it a proportion. You could times it by 100 and make it a percentage. Either way you decide to format the answer or interpret it, this is what they would be going for in a MyLab question, but the interpretation might be something along these lines. Either focus on the percent or at as a proportion. You might say the proportion of the tracer remaining after a week is that 1.5 times 10 to the power negative 4. So it's almost completely effectively gone. After 2 weeks, it probably can't be measured at all. And it's, that might be tough to measure as well. I don't know if they could really detect that to that level of precision if they had to, for some reason, do a blood draw and determine how much of that tracer is even left in your blood. That's a whole nother lab scientific question itself. So with that half-life, the exponential decay, this is going to zero rapidly in terms of days of the week going by. Well, with this problem down, again, we only focused on this, the fractional decay factor. For some questions, we do have an initial value, so we combine that to find a new value. But this problem, just like the first couple examples on the notes, didn't have the initial amount. We're just wondering how fast is it decreasing, essentially, when the question is in this format. So let's change it out to a different kind of problem. This one looks like it's a ecology kind of problem. We're looking into a population of critically endangered mountain yellow-legged frogs. So a real species, critically endangered, unfortunately. It's estimated to be at 8,000 individuals. But we would consider that to be an initial amount in our formulas. 8,000 is the initial amount. And we're told that it's also, unfortunately, rapidly declining with a half-life of 12 years. And the major challenge for this particular frog is ongoing spread of that fungal pathogen. I should have practiced that. Cythridiomyces. I'm just guessing on the pronunciation. So this frog is going through some pretty tough challenges in its environment. And the deadly fungal pathogen is causing a half-life for the population size to be about 12 years. So T half is 12 years in this problem for the half-life. And if nothing changes, if the fungal pathogen continues to afflict this species in the same way, if the half-life remains consistent, in other words, we want to estimate how many individuals are projected to remain in 15 years, and to do another projection in 36 years. This is pretty similar to what we did with our projection for CPI. We made a big assumption that the inflationary rate stayed at 1.7%, and we wondered what the CPI would be under that assumption in 2025. And this is the same kind of idea. If the initial population is 8,000, we don't have the actual decay rate as a percentage given. We have the half-life, but we're still making just as big of an assumption. We're assuming the pathogen afflicts it at the same way, that there's no extra kind of forces affecting this species. So the half-life stays consistent year after year, well into the future of 36 years for our projection. So it is a what-if question, just like before with CPI, but these kind of problems can be still very informative. Based on this decay model, how many individuals are projected to remain after 15 years? We need to use this formula. Let's cite it down on paper. The new value or amount is going to be equal to the initial. Actually, let's keep it a amount. Let me double check the wording there just to keep it similar. No, they go with value. Let's keep it to new value is going to be the initial value multiplied against the fractional rate at which it decays, which is 2 to the power of t divided by t double. So that's the formula we're about to use. We have from this part of the problem, t is provided to be 15 years. That's a compatible unit with a half-life of 12 years. So it's just a little bit more than the half-life, which means if this was a question right at 12 years, we don't really need the formula. It's going to be half of that directly, just 4,000. So it's the fact that 15 years have gone by, we really need the formula, and we're expecting something just below 4,000. So let's say down here, the number, let me keep the formatting the same with the color coding. For the new value, let me put in the number of frogs. Again, the specific species, the mountain yellow-tailed, yellow-legged frog, is going to be the initial amount, 8,000 rather, frogs, multiplied by fractional decay rate, which is 2 to the power of the number of years that have gone by, 15, divided by the half-life of 12 years, telling us a little bit more than one half-life has gone by. And this will give us the population size now at this time. So going back to Desmos, hang on, there's a mistake here. I think I made the same mistake twice. Sorry for this error. I'm looking into the doubling time formula, but keep in mind, the actual formula we're using for half-life goes like this. That's a critical error. Make sure you don't make that silly mistake there. There's got to be a 1/2 in the problem. Let me try to emphasize that a little bit better. Times the power 1/2 to the exponent of t divided by t double. So 1/2 again over here. Okay, 1/2 in that spot. Again, sorry for the distraction on that one. I think it got a little bit familiar with the wrong formatting. 1/2 for half-life, 2 for the exponential growth. So with that better formula thrown in, take the 8,000 initial amount times 1/2 to the power 15 divided by 12. I'm really thinking about the context. You'll know right away that something really silly went awry with this if you put in 2, because now you're saying there's about 20,000 frogs, but that does not match the context, right? The population is declining, and this is an exploding population instead. So there's some protection in the calculator when you get the number out to see if it fits the context as well. On this problem, we're rounding to the nearest whole number, the nearest whole frog. So that rounds up to 3364. Frogs. So if nothing changes and the half-life remains constant at 12 years, in 15 years, a little bit more than one half-life, meaning a little bit less than 8,000, this is the number of frogs that we're expecting. Well, any questions at all, folks, with the first computation there? Okay, part B, you actually have options on part B for how you would like to calculate this one. I think the formula is nice and it's a good to practice. So let's do it through the formula. But if you've spotted the shortcut on how to do this, don't hesitate to throw it out there over voice or in chat. Because if you notice something particular about the time here and the half-life, really it's a short answer. So let's start off by just reusing the formula just to see how it goes. Time, 36 years on this one. So that means the number of frogs in 36 years is going to be the 8,000 frogs initially times 1/2. Let me put this in that color once again, just to emphasize it. For exponential decay, it's got to be that 1/2. Take 36 years, divide by the half-life of 12. Then once we plug this in, here's what we'll get. In the calculator, it's 8,000 times 1/2 to the power of 36 divided by 12. And it comes out to a dead on even 1,000 frogs. So here's the 1,000 frogs. Projected to be remaining after the 36 years have gone by. Oop, that's the wrong tab. Let me fix that. Here we go. Well, any questions at all, folks? Getting the 1,000 frogs on this one? Okay, and we mentioned this problem actually really didn't need the half-life formula that we're looking into for the new value whatsoever. This problem had a really nice time frame given to us. If the half-life is 12 years and 36 years have gone by, that just means 3 half-lives have occurred. So if we have an initial population size of 8,000, divide it by 2, and that's 1 half-life. Divide by 2 again, or just raise it to 2 to the power 2, or 2 times 2. That's 2 half-lives going by. Multiply by 2 again, 3 half-lives have gone by. And so that's why it's exactly 1,000 frogs. So really, that's all we had to do in this problem to get through the answer. But it's good to see it the formulaic way as well. So exactly 3 half-lives. Let's just make this as a comment, since sometimes it's nice to have a shortcut. 36 divided by 12 is 3. 3 half-lives have gone by. So we have a shortcut. Take 8,000, divide it by 2 to the power 3, which is just 8,000 divided by 8, to get 1,000 frogs. That's kind of rare for the question to line up directly with the half-life. Usually they're awkward, like 15 years, maybe 27 years, random values like that. But if you can spot the shortcut, then that's kind of satisfying in a way to just crank it out in that one step there. Well, that's the round up for dealing with this brand new equation. Getting the new value for exponential decay with that one change there. Don't do as I did, make sure you put in the 1/2. But the problem with all this is, once again, the same problem we had with exponential growth. Sometimes problems have a doubling time, but I would say it's kind of rare for someone to tell you what a double time is. Usually it's more common to be told what the growth rate is, or what the decay rate is instead of just a doubling time or a half-life. So if we had the decay rate, much like some of the examples we saw in the Unit 8A, we would want to know what is the half-life so we can reuse this formula once again. So that's what the next formula is going to be all about. Notice something kind of exceptional about this formula. We go back to our prior formula for doubling time. Let's see, where did it go? There it is. Here's our formula for doubling time. If we're looking for something decaying exponentially, this is the rule of 70 once again. Our author just didn't give it that name. The approximate half-life formula says, for quantity decaying exponentially at a rate of p%, that per time period, the half-life is this. Exactly the same as the doubling time. That's kind of fantastic in a way. And it seems random, right? How is it that we're getting away with using the same exact formula if the exponential growth is so completely different? The reason this works out is because when you use it in the formula down below here, oh, hang on, that's too far. When you use this formula for half-life down below, it works out correctly once you put in that factor of 1/2. That's what makes it come out right and make things actually decay rather than grow. So it is suspicious. It's exactly the same formula. The context is exponential decay. And so when we know it's a decay problem, we'll just make sure to use that 1/2 factor instead of the doubling factor times 2. The thing to be wary about, same comment as before, is just make sure, drop the percent symbol, but do not, this is weird again, convert to a decimal. So that's the only warning. This half-life formula also has the same shortcoming. It is an approximation. We're honest right there with the squiggly lines instead of direct equality. It's approximately 70 divided by p. The approximation can fall apart. If it's decaying faster than a rate of 15%, then we have a problem. And so we have to watch out for that scenario there. Well, aside from that, it's a fantastic formula. It gets things to work out just right. Any last questions about the formula before we give it a try? Okay, well, here's our next context. Looking at the time, this could be our last problem for the day. Let's see where we end up on. We're talking about the island of Borneo. I have no idea where that is. Let's see if we can get a better mental picture on this one. On the last example, we knew we were dealing with frogs and we're told their legs are yellow, so we probably had a mental image there. But for the island of Borneo, this is, I do not see where it is. Oh, somewhere right around here. So this is the island, it looks like. This looks like it's around the Malaysia, Southeastern Asia region. Okay, so that's the island. We've got a mental image. It's kind of a nice part of the planet, nice and warm. The island of Borneo is experiencing some of the highest deforestation rates in the world, they're telling us. Deforestation is causing the total acreage of Borneo lowland rainforests to decline approximately 2% per year. And apparently by the context of this problem, that sounds small, saying 2% per year, but that's actually at the higher end of deforestation, declining or decreasing by 2% of its total area. And this problem will round to 1 decimal place, and we have a decay rate of that percentage. What we want is the approximate half-life formula so we can address follow-up questions, like say this one that has an initial value put into it. Okay, so far we have a percentage. That's P right there as a percent. That means P in this problem is just 2, not a 0.02. If you put in a 0.02, that's great in the right kind of context, like say compound interest. But here it would mess up the rule of 70, the way our author has stated it. So we want to know the approximate half-life of the area of this forest coverage. So we go, citing the formula above, T half, will be approximately equal to, take 70, divide by 2 for the value of P. That's a faster computation. This will come out as 35. We should definitely give a unit to this, just in case a follow-up question has a unit mismatch. We'll notice right away. If this says 2% per year, the unit on this one will be years as well. So it'll take 35 years at this decay rate for half of the coverage of this rainforest to vanish. Well, any questions at all, folks, using that formula there so far? Okay, now we have a follow-up question. The follow-up question isn't asking for a decay factor. Instead, it gave us an initial amount, an initial value. And we're saying now, if 40 years have gone by, but the half-life is 35 years, how much of this is remaining? It's going to be close to 200,000, but it's going to be below that. Kind of similar to what we were looking at with the frogs problem, because this is just a little bit above the actual half-life itself. If this said 70 years, then that's going to be a quick operation. Just divide by 2 to the power 2, divide by 2 twice, in other words. But here, this is a good one to write down just the full formula. So let's cite it here just for practice. The new value is going to be equal to the initial value. Here's the moment of truth. Make sure to not forget that you multiply by 1/2. Something is decaying exponentially. So go 1/2 to the power of t divided by t half, the actual half-life itself. So this is the fractional amount it's going to decay by. Multiply it by an initial value, and we'll show how much is projected to be remaining in that 40 years. Like before, these are just estimates. We're assuming that nothing changes in the governmental policy of the nation of Borneo. If it continues to decline at 2%, then we'll have a projected amount. So let's say projected. Oh, once again, let me keep the color coding the same. Let me put this in black to emphasize it's the new value. The projected rainforest coverage in 40 years will be, take where it's starting at currently. So 2026, approximately 400,000 square kilometers. That's a 2 there. Let me fix that penmanship. Multiply that against 1/2 to a power. This is in t equals 40 years, and we kind of indicated it twice here as well, but let's just say that to emphasize t is 40. So put 40 here, divide by half-life, which we came up with at 35 years. And from that, we'll get a value out. So now all we need to do is shove it back into the calculator. We've used this calculator quite a lot in this unit. So 400,000 times 1/2 to the power of 40 over 35 gets us this. We're rounding to 1 decimal place. So 181,144.7 kilometers squared is projected to be remaining in 40 years if they continue to have deforestation at 2% per year. That's impressive. I mean, 40 years is a long time, but this means if you are an island resident of Borneo, then in your lifetime, you're probably going to see it completely cut in half and worse in 40 years. So that would be absolutely noticeable. And again, it's kind of impressive. 2% sounds small, but on these timescales, that is really, really impactful. Well, any last questions or thoughts, folks, completing this example here? Okay, again, we mentioned before, this section is a little bit tricky. There are a good amount of formulas, but the more you study the section, the more you practice the problems, you're going to notice a lot of these formulas, they are almost identical. You just have to be really careful, like I was kind of having an issue with of making sure it's a 1/2 that goes in whenever it's a half-life problem, a 2 goes into there whenever it's an exponential growth problem. If we're looking into the approximate half-life or the approximate doubling time, the formula is absolutely identical. All that's changed here is whatever we called it, a half-life or a doubling time. So that really helps out quite a lot with the formulas. We'll practice these a little bit more when we come back on Monday. But the main things we're going to do after another follow-up question, we're going to get to that doomsday glacier eventually, is we need to start discussing logarithms a little bit. This is going to get us a little bit well set up when we get into the last unit of chapter 8, dealing with log scales. So when we look into logarithms, the major purpose for that is our so-called rules of 70, they break down. You have to have growth rates and decay rates below that value or at that value at its worst. And even if it's, say, at 2%, that's still an approximation. These are really serious questions. These are real scenarios. So sometimes it's better to not approximate at all. And so we're going to also look into on Monday when we come back, the exact doubling time formula. It's going to use logarithms, and we'll look into the exact half-life formula. They're almost the same. One happens to have a negative sign. And using this information, we can give more accurate computations. So these will be the last kind of questions we're going to look into on Monday. Well, I think this is, again, probably a good stopping point for us. This next question will take more than our 3 minutes and some change remaining on the clock. Any last questions or thoughts at all, folks, before we call it a night? Okay, well, have a great night, everyone. Have a great weekend, and congratulations again. We are 75% through with the semester. The last 25% will feel like it kind of goes fast. So double check Canvas. I'll be posting over time on Friday information for the third exam if you want to start studying early. I'll be able to post the coverage, the first version of the sample exam questions pretty quickly. I'm making my second version of questions from scratch, so that part might take a little bit of time. It could extend over into Saturday. I'll try to get them posted as soon as possible. But have a great weekend, folks. We'll see you all next Monday.